All right, so in this video, we're going to be looking at just practicing with these low structures. So we're going to look at a handful of different substances. We can see a couple of them here. So if you want to, as I go through these different slides, just take a minute when I first show these different examples to kind of pause it, work on them on your own. Then you can unpause it, just kind of skip around as you need to see the answers. If you get anything wrong, you can look at an example more. But I'm just going to kind of start going through these. And with them, I'm just going to go through them in order. But the process for all of them is going to be the same. We get the number of valence electrons we have to work with, figure out what element goes in the middle, distribute those electrons as needed to typically fill the valence shell of all of those atoms. But remember, in some cases, we may have an odd number of electrons. We may have a electron that's or an element that's electron deficient, such as boron. We may have elements that are expanding the octet. So we won't always just have those 8 electrons around the elements or 2 around hydrogen. But we just want to get the optimal structure. So in some cases, we may need to check the formal charges of these as well. And that's always a good thing to do. But just starting with the first one, we've got silicon with 4 hydrogens, so silicon tetrahydride. And like I said, the first thing we need to do, figure out how many electrons we actually have to work with. So for silicon, group 14, going to give us 4. Hydrogen, we've got 1 from each of them, but we've got 4 total. So we've got 8 valence electrons to work with. So with this silicon tetrahydride, this is going to be a relatively simple structure because all we're going to have to do is put the silicon in the middle, and then we'll just bond it with 4 hydrogens. Because remember, with hydrogen, it only needs 2 electrons because it's in the first period. So once it has that single bond, hydrogen's happy. It'll never have anything else beyond that single bond. And then with the silicon down in the middle, we just have 4 bonds around it. But that's how it's getting its 8 electrons because those bonds count for both atoms involved. And then if we calculated the formal charge of this atom, it would just be of these atoms, I should say, it would just be 0 all the way around. So this is going to be the only structure we could wind up with here for silicon tetrahydride. And then with the next one, okay, we've got a ion, so we've got a carbon, a hydrogen with 2 oxygens. So again, we need to calculate the electrons. So we'll get 4 from carbon, we'll get 1 from that hydrogen, and then we've got 2 oxygens that'll each give us 6. So we're going to have 17 total. But then just note, we've got that negative charge here. Electrons themselves are negative, so we've got an additional electron. So we're really just going to add 1, and now we've got 18 electrons total to work with. So remember, with these ions, the only thing that changes in the process is just when we're calculating the valence electrons, we've got that one extra step to account for that charge. And then at the very end, once we do get the structure, we're just going to put brackets around it. And then whatever that charge is, we're going to put to the top right. So for this one, we're thinking about what atom is in the middle. So remember, hydrogen can never be in the middle. And then carbon pretty much always will be a central atom. And then even if we just think about carbon versus oxygen, oxygen is going to be more electronegative. And we're typically going to have the less electronegative atom be the central one. So in this case, we can start with the carbon in the middle. We'll do a hydrogen, an oxygen, and then a second oxygen. And then we're just going to fill in these valence shells. So for each of these oxygens, since they have 2 electrons from that bond, we'll go like that. And then remember, again, hydrogen just needs that single bond, so we don't need to add any of the dots around hydrogen. But now if we look at this structure, count how many electrons we've used. We've used 6 electrons in those 3 bonds total. And then we've got 6 more around each of those oxygens, so we've used 18 if we counted them all up right here. That's how many we needed to use. And those terminal atoms have a full valence shell. But that central carbon only has the 3 bonds to it, so it only has 6 electrons. It's missing 2 more. So what we're going to need to do in this case is remove one set of the lone pairs from the oxygen, and then just form a double bond. And like I said, we'll put brackets around it. and then put the structure to the top right. But with this, I think this was actually one of the examples we had when we were looking at resonance. Because with this structure, we would have resonance. If you think about it, I could have also drawn the double bond to the other oxygen. So with this one, typically we would have both structures shown, and we would just have an arrow like that in between them. So on the right-hand side, if I had more room on the screen, I would draw the other structure for this resonance, but I would just have the double bond going to that other oxygen in that case. But again, if we check the formal charges here, we would see 0, 0, 0, and then -1. And that makes sense because the ion itself had a -1 charge. So the sum of these formal charges have to balance out to whatever that charge is. So in this case, this is going to be our optimal structure. And then the next one, again, we've got a ion, so we've got to focus on that charge. We've got NO with a positive, so nitrogen, oops, that won't give us 4, it'll give us 5. Oxygen will give us 6, 11 total, oops, not -10, just -1 to give us 10. But again, yeah, since this charge is positive now, remember electrons are negative, so if we have a positive charge, that means we lost one of those negative pieces, we've lost one of those electrons. So when we've got a positive charge, we're going to subtract electrons. So in this case, we're only going to have 10 to work with. And with this one, we only have 2 atoms, so it's not really important which one's the central one, because there's not really a central one. It's just left and right, and then even that doesn't matter, because you could think about it just looking at it from kind of the opposite side of the screen. So if you had a reverse perspective, left and right would switch, so that's not important either. So I'm just going to do NO just to keep it with the formula, but you could have O on the left, N on the right, and it's going to be the same thing. But now when we're looking at it, we can do a single bond, and if we're thinking about these 2 atoms, oxygen is going to be more electronegative. So I'll just put 6 electrons around oxygen first, and now we've used 8 total, 2 from the bond, and then the 6 that are just on oxygen. So we only had 10 to work with, so I've only got 2 more I can place around that nitrogen. But then by doing this, we filled the valence shell of oxygen. Nitrogen's only half filled. So again, we're going to have to go back, form some multiple bonds. And in this case, since nitrogen needs 4 more electrons, we can't just form a double bond, because if we only do this, that gives nitrogen 2 more. Oxygen still has 8, but because nitrogen only had 4 to begin with from the original kind of structure, now it only has 6, so it's still not a full valence shell. So we've just got to form a triple bond by removing a second set of lone pairs from that oxygen. And now when we look at it, the triple bond represents 6 electrons that count for each of those atoms. And then nitrogen's getting the 7th and 8th from its lone pair, oxygen getting its 7th and 8th from its lone pair as well. And it uses 10 overall. So we're just going to put this structure in brackets and then put the positive sign there. And then the final one on this slide is going to be oxygen difluoride. So oxygen, group 16, oops, going to give us 6 valence electrons. Fluorine, we've got 2 of them that are halogens, so each of them are going to give us 7 for 14 from the fluorines, so we'll have 20 total to work with. And then with this one, typically, like I said, the less electronegative atom is going to be the central one. And oxygen is going to be more electronegative than pretty much everything, with the exception of fluorine. So this is going to be the case where we actually see oxygen in the middle, and then we'll have the 2 fluorines on the outside. And again, just like always, we can fill in the valence shell of those terminal atoms. So we'll put 6 more dots around each of these fluorines to give them 8 valence electrons total. And now when we've done this, we've used 16 electrons overall. Again, 6 on each of the fluorines by themselves, giving us 12 total. And then we've got 2 in each of these bonds for 4 more, so 12 plus 4, giving us 16. We had 20 to work with, though, so we still have 4 electrons available. So what we can do is just add 4 more dots to this oxygen. And remember earlier I discussed kind of how we can quickly just calculate what the formal charge of an atom is going to be. Look to see what group it's in. Think about how many bonds it wants to form. Fluorine, group 17, all of the halogens just need 1 extra electron. So they just want to form one bond. They just need that extra piece. So by forming that one bond, they gain that one extra electron they need. So with the halogens, if they have 3 lone pairs and just a single bond, they're going to have a formal charge of 0. And then oxygen in group 16, one to the left now, it needs 2 electrons to fill its valence shell because it starts with 6. So it wants to form 2 bonds. And that's why a lot of the times we're going to see oxygen either in just a double bond or something like this, where we'll see it's attached to 2 things with single bonds. But in either case, because it's got the 2 bonds it needs to gain those 2 electrons, we would see the formal charge of oxygen here would also be 0. So this is just going to be our optimal structure. And then just note, with these ones, we just had the regular octet for each of them. The only one that can exceed the octet would be silicon, but there was no need to do it in that case. Because it's period 3, it can exceed the octet, but we didn't need to do it with silicon. So it's just all of these first couple of examples, they were relatively straightforward because it was just kind of the octet itself. We weren't exceeding the octet, we didn't have an odd number of electrons, we didn't have an electron deficient atom at all. But this is going to be the same process we'll always use. Okay, and then we've got a couple more here. So this tells us that NASA's Cassini, I'm not even gonna, Huygens maybe, I don't know, mission detected a large cloud of toxic hydrogen cyanide on Titan, which is one of the moons of Saturn. Titan also contained ethane, acetylene, and ammonia. What are the Lewis structures for these molecules? So with these ones, especially with like ethane and acetylene, the way that they're showing those formulas, H3C, CH3, or HCCH, is a little different than we would normally do. A lot of the times we just group each element together individually. So we'd have like C2H6 or C2H2 for acetylene. But with these ones, they're kind of showing it in more of the organic structural formula. So it's actually kind of showing what's bonded to what. So remember earlier I mentioned organic in one of the previous videos, I mentioned organic chemistry, the study of carbon, and there's different ways we can represent those structures. So there's those skeletal structures where the carbons and the hydrogens are actually implied. So we just use kind of like the corners and the ends of lines to represent where those carbons are going to be. But when we're writing the formula out, sometimes instead of just doing C2H6 or C2H2, we write out kind of a structural formula. And in this case, what it's representing is these carbons are all going to be attached to each other. And then those other pieces are just going to be attached to the carbon. So in this case, in each of them, we're going to have the 2 carbons bonded to each other. And then in the case of ethane, we'll have 3 hydrogens attached to one of those carbons. We'll have 3 hydrogens attached to the other. Or in acetylene, we'll have the 2 carbons bonded to each other. And then also coming off of each of those carbons is just going to be one of those hydrogens. And with those ones, we can kind of approach it in a different way, and we'll see that as well. But with ammonia and hydrogen cyanide, those are going to be kind of just how we would typically go about it. With hydrogen cyanide, if you want to practice on your own, if you don't remember that one, we did see that example earlier. So I'm just going to kind of draw the structure. When I was going through the initial steps we use, hydrogen cyanide was one of the examples we looked at to talk about multiple bonds. So if you want to practice with that one on your own, if you don't remember seeing that one, still a good one. I'm just going to show it though, and then I'll show how we can get the other. Even ammonia, we've kind of already seen an example of earlier on too, I believe. But I'll show that one in ethane and acetylene as well. But with hydrogen cyanide, what we're going to see is it's just going to be and then even with the ammonia, that one's relatively straightforward. We can get the number of valence electrons, which is going to be 8, because we'll get 5 from nitrogen. We'll get 1 from each of the 3 hydrogens. And then in this case, nitrogen will go in the middle. So we've used 6 electrons here. So the 7th and the 8th is just going to go on nitrogen like that. And then, like I said, with the ethane and the acetylene, in this case, it's kind of showing us the structural formula. So it's kind of showing us what's going to be bonded to what already. So what we need to do is just think about how are those electrons going to be distributed. So in the case of ethane, we've got 2 carbons. Remember, carbon gives us 4 valence electrons, so we'll have 8 from the carbons, and then we've got 6 hydrogens. that each give us 1. So 8 plus 6, we're going to have 14 valence electrons there. And then with the acetylene, we'll just have 10. But like I said, this is kind of already showing us what's bonded to what. So for the ethane, we've got 2 carbons attached to each other. And then off of each of those carbons, we're going to have 3 hydrogens. So when we look at the structure for ethane, this is actually going to be all we need to do. Because when we look at the hydrogens on the outside, they each have just the 2 electrons they want from that single bond. And now the carbons in the center, we've got 2 central carbons basically in this case. But each of them now have 4 bonds to them. So they've got the 8 electrons they need. And if we calculated the valence, the formal charge, excuse me, we would see it's 0 on each of these atoms. And then kind of the same thing with acetylene. We've got these carbons bonded to each other. But in this case, they each only have 1 hydrogen attached to them. So if we look at this structure now, we've used 6 electrons total. We've got 3 single bonds. Each count as 2 electrons. So we've got 4 more to work with. And again, those hydrogens on the outside are fine. Don't need any more valence electrons. They've got the single bond. But each of these carbons now is involved in 2 bonds. So each of these carbons has 4 electrons total. So one thing we could do is put 2 sets of lone pairs on one of those carbons. And now that carbon has 8 electrons around it. We've used the correct number of electrons total. But the carbon to the right of it now is still electron deficient. It's still missing 4 electrons. So what we're going to have to do in this case is just take those lone pairs and just actually use them as a double bond and then a triple bond. Because now when we look at this structure, each of those carbons is getting 6 electrons from that triple bond. And then they each have a single bond with hydrogen to get the 7th and the 8th. So now each of these atoms has a full valence shell. We've used the correct number overall. And again, the formal charges for carbon and hydrogen in this one would just be 0 as well. So when we've got a structural formula, kind of like we see with ethane and acetylene, we just want to remember that those carbons are going to be attached in a chain. And then we'll see this in the lab as well. Sometimes we'll have more than 2 carbons, but it's still going to be kind of showing us that structure. It's just not quite as clear as when we only have 2, and then we can kind of put the other stuff on each side. But it's going to be that same idea still. Yep. So you can even see with the acetylene one, I put both lone pairs just on 1 carbon to fill the valence shell. In this case, they split the lone pairs, so each of them only had 6. But either way, we need to put the electrons in the double bond there. And then if you want to practice with carbon monoxide and carbon dioxide, those structures we've seen as well as looking at different examples. So I'll leave it here if you just want to practice, and then you can see the results. But just pause the video as always, because I'm just gonna go ahead and not really show those ones, or how to get them at least, because we've already seen them. Okay. So for this one now, we've got xenon. So kind of a weird one. Xenon noble gases, typically we say they're going to be inert, they're unreactive. As you get further down that group though, as those atoms get larger, in some cases you can have them react if you have certain conditions, if you have them with something extremely reactive such as fluorine. So we can form a few compounds that contain those noble gases. But if we want to get the structure of them, it's still going to be that same idea. So in this case, I don't remember if we actually looked at xenon tetrafluoride, ZeF4, earlier, but this just comes from the textbook, and we want to figure out the structures of xenon F2, so xenon difluoride, and then xenon hexafluoride, so xenon with 6 fluorines. But with it, okay, so we've got xenon, which is going to give us 8 electrons because it's a noble gas. And then fluorine, we've got 2 of them, that'll give us 7. So for the first structure, we're going to have 22 valence electrons in total to work with. And again, if we've got a single atom of something, typically going to be the central one, or the less electronegative element, typically going to be the central one. So in either case, that's going to be xenon. So we're going to want xenon in the middle. We'll take each of these fluorines and just put them on the outside. And again, even though we've got a noble gas, we're still going to treat this process the same. It's kind of a weird compound because it contains the noble gas, but the steps to get that structure are going to be no different. So with the fluorines, change that a little bit so it doesn't look as weird. With the fluorines, we can just add those lone pairs to fill the valence shell. So now each fluorine's got the 8 valence electrons it wants. And in this process, we've used 16 electrons. 16 electrons total. So with the xenon, only has 4 electrons. We've got 6 extra electrons, though. So if we just do something like this, now we filled the valence shell of each of these atoms. But we still have 2 electrons to work with. So what we're going to do in this case, this is actually going to be one of the examples where we exceed the octet. Remember, elements in the 3rd period and below, and xenon is in the 5th period. So xenon can exceed that octet. It's got that empty D block, D subshell available. So what we can do with those extra electrons is just essentially pack them onto that central atom. And if we look at the formal charge here, so again, fluorine halogen has a single bond. So the formal charge of fluorine is going to be 0. I'm not going to go through that one. But if we look at the formal charge for xenon, it's got 8 valence electrons as a free atom. And in this case, it's got 6 valence electrons on its own. It's got 3 sets of lone pairs, and then 1/2 of the bonded electrons. It's involved in 2 bonds that account for 4 electrons. So in this case, it's really 8 minus 6 minus half of 4, or 8 minus 6 minus 2. So we're going to see the formal charge of all of these atoms now, when we exceed or expand the octet for xenon, gives us a formal charge of 0 all the way around. So we just want to remember that when we get to that 3rd period and below, we have the option, if we have extra electrons, to essentially just pack them on to that central atom. Okay, and then with the second one, kind of the same idea, just in this case, we've got 6 fluorines instead of 2. We'll still get 8 valence electrons from the xenon, but now we've got 6 times 7. So in this case, we're going to have 50 electrons total, because we're going to have 42 of them coming from fluorine, and then 8 from the xenon. And what we can do is just put xenon in the middle. And if you think about this one, just by the number of fluorine that we have, it's going to clearly have to exceed the octet, just because we're going to have at least 6 bonds to it. We may have, in some cases, you could maybe form a double bond. You may have lone pairs on the xenon as well. But it's going to have at least 6 bonds to those 6 fluorines. So it's going to have at least 12 electrons around it. So again, definitely going to be a case where we expand the octet. So I'm just going to do 6 bonds to these fluorines. And then I'll add in all of these dots if you give me a moment. But by doing this, we're going to be using 6 electrons around each of these fluorines. And then they've also got 2 from the bond. So now each of these fluorines has 8 electrons total. So 8 times 6 is going to give us 48. But again, we've got 50 electrons. So we've got 2 more we can pack on here. Sometimes the dots are a little tough to show with the stylus I have. But again, if we look at the formal charge, again, fluorine, all single bonds, 3 sets of lone pairs. So the fluorines are going to have a formal charge of 0, which means that the xenon has to be 0, since the neutral molecule overall balances out to the formal charge, or the overall charge, I should say. But if we just look at why the xenon, we'll do FC formal charge of xenon. Again, 8. In this case, it's only got 2 electrons on its own, but then it's 1/2 of the bonded electrons. It's sharing 12 electrons between all of those different fluorine. So again, we're going to see the formal charge of xenon, in this case, by expanding that octet, is going to be 0. It's just we're expanding it in a different way than we did in the previous example with only 2 of those fluorines. Oops. Okay. So this will be, hopefully you didn't see the answers if you want to work on these on your own. But these will be the last 2 that we look at for the practicing Lewis structures. And then we'll start to look at kind of how we can take these Lewis structures and get them into the true 3-dimensional shape. because these Lewis structures are only showing what's bonded to what and how the electrons are kind of distributed in terms of single, double, triple bonds and lone pairs. But they don't necessarily reflect what these molecules are really going to look like, or ions, I should say. So with the next piece where we do actually try to get the true three-dimensional shape, and then ultimately we can use that to understand the properties of those substances. We'll still be practicing with the Lewis structures because that's still going to be the first step there. It's just going to be once we get that Lewis structure, then we can go to the three-dimensional shape, then we can get the chemical properties. Which I guess, yeah, you could kind of, once you learn that three-dimensional part, you don't necessarily always need to draw the structure in 3 dimensions to understand the properties. But that's at least what we'll be doing initially. But for these ones, again, just doing the same process, figuring out the valence electrons, distribute them around, check the formal charges. And with the first one, we've got boron trichloride. So with it, we're going to have 28 electrons total, just because each of those are halogens. So we've got one one bromine, excuse me, and 3 chlorines. So 4 atoms total that are each going to give us 7 valence electrons. So just 4 times 7, giving us 28. And then we'll have the bromine in the middle because it's the less electronegative, and we only have one of them. So we'll do 1 chlorine. And then with these Lewis structures, like I just said, they don't show the true three-dimensional shape. So you could technically kind of put these at any angle you want. If you don't have the chlorines going in the same place I do, if you made like a perfect T shape, if you had one of them pointed up and then the 2 pointed at like corners at the bottom, giving a triangle, that would be fine as well. We're just with these Lewis structures, at least just showing what's bonded to what and how those electrons are distributed. But then by doing this, we can do lone pairs on each of these chlorines. So at this point, once we fill in the valence shell of these chlorines, we've used 24 electrons total. So again, we're going to have to expand the octet. We're going to add 2 more sets of lone pairs, so 4 total to that bromine to use 28 overall. And then if we check the formal charges of each of these, again, those halogens with the single bond 3 lone pairs on the outside with the chlorines are going to be 0. So the bromine has to be 0 as well. But if we calculated the bromine, 7 valence electrons, it's got 4 on its own, and then 1/2 of the shared electron, so 1/2 of 6. 7 minus 4 minus 3 just gives us 0. So we've got a formal charge of 0 on all of these different atoms. So this is going to be our optimized, most likely structure. And then the final one we'll look at here, ICl4 with a -2 charge, or -1 charge, excuse me. I guess I could have done the same thing. But we'll end up with 35 valence electrons. But because we do have that negative charge, we'll add 1 more and get 36. So then we'll have iodine in the middle. We'll do 4 chlorines and fill in the valence shells of each of them. And then by doing that, we've used now 32 electrons total. So we've got 4 more to work with, excuse me. But again, iodine is in the 5th period, so we can expand the octet 3rd period and below. So we're just going to pack those extra electrons onto that central atom. And what we'll see here is we've just got to then put a bracket around it with the negative charge there. And then with this one in particular, just looking at it, if we calculate the formal charges, we'd have 0, 0, 0, which means this iodine has to be -1. Because it would be 7 minus 4 for the electrons it has by itself, and then 1/2 of 8. So 7 minus 4 minus 4. So 7 minus 8 gives us -1 there. And with this one, typically we say the negative charge is going to wind up on the outside with the more electronegative element. So what we could do in that case is something like that. Just pause this video for a second. Somebody's at the door. Okay, sorry about that. I got distracted for a second. But with this one, if we go back, I forget exactly where I left off, but just looking at what I have here, the reason we won't see this as the Lewis structure, or at least one way you can think about it, because in this case, if we look at the formal charges, I'll use a different color so that we know green's not correct. But if we looked at the formal charges here, we would have for iodine 7 minus 2 minus 5, so yeah, 0. And then that means that the chlorine would be minus 1. But with it, if you look at it now, in the previous structure, the correct structure where it's just single bonds, then iodine has 4 valence electrons on it. Iodine's still going to be electronegative, so it's not as weird of an example as like when we had the boron in the middle and the fluorine on the outside, where boron was electron deficient. So in this case, iodine's not going to be like the difference just isn't going to be as great between iodine and chlorine. But then also, if you think about it now, with this double bond, iodine still expands the octet. Iodine now has 10 electrons instead of 12, but it's still exceeding that 8 electron octet. And then the same thing with the chlorine now. It had 8, but now when we form the double bond, chlorine has 10, which it can do in some cases, and it's in the third period, so we can expand that octet. But now both of them have an expanded octet. And then just based on the way the electrons in iodine are going to share, we're just going to see the correct structures with the single bonds and then 2 lone pairs here. So let me erase these just so we don't think that those are correct. Oops, no, this will be -1. This will be 0. But with it, like I said, starting with the hopefully that's what I had. Yeah. With the next piece, like I said, we'll start to look at kind of the 3-dimensional shape of these structures. And the reason that they're not always going to match up is because the bonds where the electrons are located are shared between those atoms, as well as the lone pairs are all going to have negative charges. So these bonds, these atoms are going to try to spread out in order to minimize those repulsion forces.